All right, let's get into it. Today, we're pulling back the curtain on one of the coolest magic tricks in all of quantum physics, superdense coding. It's a process that seems like it shouldn't be possible, like it's breaking a fundamental law of physics. But as you'll see, it's really just using a much deeper, much weirder set of rules.
Okay, so let's jump right in with the big, mind-bending question. Imagine you can only send one single particle, one tiny quantum package, to your friend. How on earth could you possibly pack two separate messages, two classical bits of information, into that one little particle? I mean, it just feels impossible, right?
And you know what? That feeling is backed up by some serious physics. There's a rule called Haleva's theorem, and it basically says, nope, can't be done. One particle, one bit of information. That's the absolute limit. But superdense coding is this incredible exception, a loophole in the rules. With the right setup, you can send 2 bits. So what's the trick? How do we get around this cosmic speed limit for information?
Well, to make this magic happen, our 2 communicators, let's call them Alice and Bob, need a little something extra. They need to share a secret resource, something they set up before they even start sending anything.
And that secret ingredient, you guessed it, is quantum entanglement. The best way to think about it is like a psychic link between 2 particles. So before the experiment even begins, Alice and Bob each take one particle from an entangled pair. Now these 2 particles are connected. They're basically part of the same system, sharing one identity. Whatever Alice does to her particle instantly affects Bob's particle, no matter how far apart they are. And this is the connection they're about to use.
Okay, let's put ourselves in Alice's shoes. She's the sender. She has a simple 2-bit message she wants to send. You know, like 00, 01, 10, or 11. Her challenge is to somehow imprint that entire message onto her single solitary particle.
And her plan is it's incredibly clever and simple. So first, she's got her particle, her half of that entangled pair. Then she decides which of the 4 possible messages she's going to send. And here's where the magic happens. Depending on the message, she does one specific little quantum flip, or twist, a quantum gate, to her particle and only her particle. Once that's done, she just sends her single particle over to Bob. That's it. Her job is done.
Okay, so this table is basically Alice's cheat sheet. If she wants to send 00, get this, she does absolutely nothing, which in the quantum world is an action in itself. To send 01, she hits her particle with a Z-gate. Think of it like flipping its phase. For 10, she uses an X-gate. That's a bit flip. And for 11, she does both. But here's the truly mind-bending part. By doing something to only her local particle, she is instantly changing the entire shared state that she has with Bob. She's transforming it into one of 4 totally unique, distinguishable states.
All right, Alice's particle is on its way. So now, let's switch over to Bob, the receiver. He gets this single particle from Alice. He now has both particles from the original pair, and his entire job is to figure out, okay, what did Alice do to her particle before she sent it?
So, Bob has a decoding recipe he has to follow, like a key that unlocks the box. He performs a specific sequence of operations. First, a C0 gate, where he uses Alice's particle to control what happens to his. Then, he hits Alice's particle with a Hadamard gate. You can just think of these steps as a way to perfectly unravel the entanglement, to translate that complex shared state back into a super simple, readable answer. After he does this, all he has to do is measure both particles. And voila, here's the payoff. Those fancy symbols on the left, they're just the names for those 4 unique entangled states Alice created. And look, Bob's decoding process turns each of those unique states perfectly back into the message Alice sent. If he gets the first state, he measures 00. If he gets the second, he measures 01, and so on. It's a perfect one-to-one mapping. It works every single time. He has just received 2 full bits of information. So let's just pause for a second. They actually did it. Alice sent 2 bits of classical information just by sending one single particle. So why does this matter? Why isn't this just a neat little physics trick? Well, it's actually incredibly profound.
The bottom line is this. Alice and Bob have literally doubled the information capacity of their channel. Now, they had to use a resource to do it, that pre-shared entangled pair, sometimes called an E-bit. But by spending that E-bit, they achieved something that's supposed to be impossible.
And hey, don't just take my word for it. The source material makes it crystal clear, and I'm quoting here. Through superdense coding, shared entanglement effectively allows for the doubling of the classical information carrying capacity of sending qubits. I mean, that's about as direct as it gets. This changes the game.
At the end of the day, what makes superdense coding so foundational is that it's not just some abstract theory. It's a concrete, real-world example, showing that entanglement isn't just some spooky philosophical idea. It's a tangible resource, a tool you can actually use to do things you couldn't do otherwise.
So where does this leave us? This amazing protocol. It's not really about making our internet faster tomorrow. It's a stepping stone, a proof of concept that really forces us to rethink what information even is.
Okay, so let's wrap this up. What are the big things you need to remember? First off, superdense coding is a real way to send two classical bits using just one qubit. Second, and this is key, it's not a free lunch. It requires one pre-shared entangled pair to work. Third, this is what allows it to get around that normal information limit set by Holovos' theorem. And finally, it's a powerful piece of evidence that the quantum world has resources that let us do things that are flat out impossible in our everyday classical world.
And that leaves us with one last big question to chew on. We've just seen how entanglement can completely bend the rules of how we send information. So it really makes you wonder, right? What other unbreakable rules of physics are just waiting for a new quantum trick to come along and show us a way around them? Something to think about. Thanks for tuning in.